Hi everyone, welcome back to Curtitus Math. So today I wanted to go through the linear function, since this is one of the most important things you learn in high school math, and it comes up a lot. So it's really important to understand what this means, what the different variables represent, and how that affects a linear function. So here we have the general rule for a linear function. So you have y equals ax plus b. If you go to a different school, then you might see y equals mx plus b. They mean the same thing, but my students are more familiar with ax plus b, which is what I will be dealing with. So I'm just going to erase this over here. So here you have your dependent variable. So y equals a, which is your rate of change or your slope. So both of those things mean the same thing. Rate of change, also known as slope. So this is how much your function or your line is changing for every value of x that you go up by. So every time you increase x, it will change by this much. So when you actually have a linear rule written out, it would be something like y equals 4x plus 5, right? So this would mean that for every time I go up by an x, I go up by 4. So this describes the change, the way that the line is changing. And then plus b, your b represents your initial value. So this is your starting spot. So we'll take a look at this specific example, and we'll actually, do we want to leave it like that? Yeah, we'll leave it like that. Okay, so, oops, I meant to be writing. So here, let's make a nice little graph. And I'll change this to graph paper. It's a little bit nicer. Okay, so our x-axis is always our horizontal axis, and our y-axis is always our vertical axis. So here, since we'll go up by 2's. I think that would work well. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That should be enough. And then over here, we'll also go up by 2's, just so that it's consistent. Your scale on your x-axis and on your y-axis, they don't have to match. They can if you want them to, but they don't have to. 15, 20, 22, 24, 26. We'll stop around there. Okay, so now just to see what happens here. So there's multiple ways that you can graph a line. You can create a table of values. So if I wanted to kind of get an idea of where points on this line would be, I can find my values of x and y. So here, you get to pick. You get to pick an x, and then you put that x in here, and then you find the y that goes with it. So this line, 4x plus 5, that's made of many, many, many points, right? And you want to have an idea of what the line looks like. So here I'm going to say, okay, well, where is this line when x is 0? So I'm going to put 0 as x. And then what you do is you take this rule and you put 0 in the space of x in order to find the y that goes with this x value. So here I'm going to get y equals 4 times 0, because I'm replacing my x with 0, plus 5. 4 times 0, that's 0, plus 5. 0 plus 5 is 5. So the y that goes with this x of 0 is 5. And I'll put that 0 in blue so we know where it came from. Okay, and then you can do that same thing with a whole bunch of numbers. So you can pick x is 1, then you can pick x is 2, you can pick x is 3, and you get all those values and you can fill out your points. So we'll do 2 of them. So here we'll have y equals 4 times 1 plus 5. 4 times 1 is 4, plus 5, we get 9. So this is 9. And we have, see, y equals 4 times 2 plus 5. So y equals 8 plus 5, that gives us 13. So we'll get 13. And then we'll actually see a little bit of a pattern here. So now we're going to take these points. So this is an ordered pair. They come together. They're a coordinate. So our coordinate here is 0 on x, 5 on y. This coordinate is 1 on x, 9 on y. Then this one here is 2 on x, 13 on y. So we're going to find those coordinates. So 0 on x, that's over here. This is where x is 0. And then you go up to find y is 5. So that's going to be right over here. I'm going to put a point right here. Then we're going to go to x is 1. That would be here, halfway. So at x is 1, we have y is 9, which is halfway over here. It's going to be right in the middle of that square. And then at x is 2, which is here, we have y is 13, which is halfway between 12 and 14. So that's right over here. And now we have a good number of points. We can connect these dots. I'm going to make a nice straight line right through them. And the thing is that your line doesn't stop here. This is not the line. The line is infinite. So lining these points up is just so that we can have a good idea of what our line looks like. But the line actually extends all the way in both directions. And now having graphed that line, we can take a look at, well, what would x be when x is, what would y be, when x is 3? Well, now we can go to x is 3, now that we have a good idea of what the line looks like, and actually just travel right up and see, well, where does it hit? It hits right over here at y is 17. So we can figure out that y would be 17 just by looking at the graph. And actually, now we can visualize what this rate of change of 4 really means. So if we remember our definition of rate of change, we said that it was the change in y over the change in x, which means that's our vertical change over our horizontal change. And we always write this as the simplest way. I don't know if that made sense. The most reduced fraction, I should say. So here we're saying 4. We do mean 4 over 1. And that fraction is equivalent to 8 over 2. Because if you multiply the top and the bottom by 2, you get 8 over 2. So these two fractions are equivalent. And you'll see why I'm deciding to write it as a fraction, because it makes a little bit more sense when you visualize it as the vertical change over the horizontal change. So we're kind of going to zoom in right over here to see, and I'm going to focus on these 2 points. So this point and this point. So on these 2 points, I have gone across by 1. And I have gone up. Actually, there, I don't want the arrows in both directions because I've gone from left to right by 1. And then I have gone up, well, from 9 to 13. So I've gone up by 4. So my vertical change, which is what goes on the top, the change in the y, my vertical change is 4. And my horizontal change, which is my change in x, that's 1. And that's where I get this 4 over 1. So I'm going to highlight these in yellow so you know that's where that comes from. Now, the reason why I decided to show you this 8 over 2 is because this is an equivalent fraction, right? So these two are essentially the same thing. My rate of change, I have not changed my rate of change. It's the same thing. These are the two same slopes. So if instead I decided to look at this point compared to this point, well, now I've gone across by 2. And I'm just going to take these away so we can look at that. And I've gone up from 5 to 13. So I've gone up by 8. So now my vertical change is 8 and my horizontal change is 2. And that's why these are equivalent. They are on the same line. The slope is the same. The angle of this line, the steepness of this line is the same. So that's where the 4 comes from, and that's how the 4 affects the way that this line functions. And now to look at the 5. So what's special about this 5 is this right over here. So this function has a value of 5 when we give x a value of 0. And that's because this is what we call the initial value. It's our starting spot. It's where we start on y. And if we look at our graph here, this line intersects the y-axis at a value of y is equal to 5. So it's our starting spot. So right over here, that's the initial value. Okay, and in class we've looked at 2 special cases of linear functions. So this is what we call a partial variation. So partial variation, and I'm going to point specifically to this, because in a partial variation, we have a value for rate of change, a non-zero value, and we have a value for initial value that's also non-zero. That's what we mean by partial variation. We have a steepness, we have a starting spot. So the 2 special cases of our linear function, so we'll say special case 1, special case, we'll just give it the title, so constant function, we've seen this. This is your same rule. So we have not changed the rule. It's just that this is the special case of this rule where rate of change equals 0. So you have no rate of change. And instead, you end up just having, so as a result, y equals b. And in class, we've called it y equals c, just for c to represent the word constant. It doesn't really matter what letter you put there as long as you understand that it's just y equals a number and just a number. It does not change. So if we were to graph this, and I'm not going to make as big of a graph since it's not a very interesting function to look at. So we have x, we have y, and we'll just go by 2's again. 2, 4, 6, 8, 10. So if we wanted to look at the same kind of values, we can say y equals 5. But we'll use 4 since that's easier. Y equals 4. So here at y equals 4, it just means that y is 4 and there is no change. So if I forced myself to actually write this whole thing out and put in the x, well then this would be, move the 4 over, 0x plus 4. There is no change for every x. So this line looks like just a straight line at 4. It's constant. Ooh, make a straight line. There we go. Perfect. So it's constant at 4. It doesn't matter what the value of x is. It will always, always be 4. It is not changing. Okay, and then our other special case is a direct variation. So here again, we have our y equals ax plus b. What's special about the direct variation is that now initial value is 0. So you have a starting point of 0. So here I'm going to go up by ones just so that it's a little bit easier to visualize what's happening. Oops. That should be 11. That should be fine. So this is x, this is y. So we'll go with our same slope as earlier, so 4x. Just now in this case, we have 4x plus 0. We are no longer starting at 5, we are starting at 0. So our first point is this 0, and we are going up by 4 for every 1. So if we wanted to remember that, over 1, so your vertical change is 4, your horizontal change is 1. So from this point, we go up by 4, we go across by 1. Go up by 4 and across by 1. So this line will look like this. And you can also extend that the other way, since the lines are infinite. So these are the special cases. You have when your line goes through 0, your initial value is 0. When your line is horizontal, it has an initial value, and it does not have a slope. It has a slope of 0. And then when you have a partial variation, your line goes through an initial value, which is a number, and it has a rate of change. So it's changing for every value of x. Okay, so in the next video, we're going to go through the ways that changing your rate of change and your initial value changes the way that your line looks. So we'll look at that in the next video. See you there.